The idea of establishing a manned space station in orbit around the Earth is not a new one. In the 1920s, the Russian Konstantin Tsiolkovsky, the undisputed grandfather of astronautics, imagined a space station where men could live. In 1971, the Russians sent the first space station into orbit, named Salyut-1. The Americans responded 2 years later with Skylab. Then, in the middle of the Cold War, in 1975, the Russians and Americans proved that space cooperation was possible with a joint Apollo-Soyuz mission.
After Apollo-Soyuz, there was a pause in the manned spaceflight programs in both the USSR and the USA.
In the mid-1980s, space cooperation was no longer. The Americans had the shuttle, and the Soviets were dominating manned spaceflight with the Mir station. The USA was planning to build its own station, but given the mammoth size of the task and the cost involved, the Europeans, Canadians, and Japanese came on board. With the collapse of the Soviet bloc, Russia was also invited to join the adventure, and the result was the ISS. Everyone involved committed to sharing their knowledge and supplying part of the station. The construction process was simple. 15 modules would be built on Earth and then assembled in space.
In fact, the space station is the biggest plug-and-play that has ever been made.
The scope of the project was immense.
Today, we still talk about the pyramids with admiration. And the ISS is the same. In the future, we'll talk about the ISS like we talk about the pyramids.
The space builders entered the frame in 1998, when the first American module was anchored to the first Russian one. Over the space of 2 years, more and more missions set off to build the station and prepare for the arrival of its first permanent residents. On November 2, 2000, cosmonaut Sergei Krikalev officially became the first resident of the International Space Station.
The first thing we had to do was to turn the lights on. We had to establish the link with Earth, and I had to find a cable hidden behind a panel. And then we could do the first report. Yes, the first thing we had to do was turn the lights on. After that, we plugged in the service module systems. We started the unit for creating air, for purifying the carbon dioxide, and ventilating with oxygen. They were critical moments. If we hadn't been able to get that going, we wouldn't have been able to stay on the station for long because the reserves in the Soyuz vessel were very low.
Building the station took 115 launches to bring the modules and teams into space. Canada provided a key element in the shape of a robotic arm. 17 meters long, it is used to move modules, supplies, material, and even astronauts. The fruit of international cooperation, the ISS gradually took shape in the sky.
We designed every mission so that if something didn't work, we would put it back into the shuttle and we'd bring it back home, but we never had to do that. Everything worked up there, and it was amazing.
Especially when you consider that many components of the space station never were tested together on the Earth and integrated only on paper.
Of course, it was all theoretical, and I was pretty surprised to see that we got it fully deployed. It's an absolutely extraordinary example of technological prowess.
The construction and operation of the International Space Station is the most expensive project ever undertaken by humankind, costing some $150 billion.
Firstly, it's not a huge amount of money, and what we're getting in return is a vast amount of scientific knowledge and understanding that is benefiting people back here on Earth. And if nothing else, it's an incredibly valuable insurance policy for the future.
From Earth, you can now clearly see this giant construction set that shines so brightly in the sky.
The reason it's so bright is because of the massive solar arrays. The surface area of the solar arrays provide such a great reflective surface for a viewer on the surface of the Earth. And it's through those solar arrays that we capture the sun's energy, produce electricity, and charge batteries that are then discharged when we're on the night side of the Earth.
When fully deployed, each panel is 73 meters long. They are permanently angled to face the sun, and each one is comprised of more than 32,000 solar panels to capture energy from the sun.
So the solar rays articulate, so as we orbit around the Earth at 4 degrees per minute, the solar rays articulate at 4 degrees per minute to continue to point to the sun. We also have, because of the orbit that we're in, we have a change in what we call the beta angle, and that means the solar rays have to articulate in this degree of freedom as well. And we have joints that do that, and the computers track the sun and then control the solar rays accordingly.
Together, the solar panels from the ISS could supply the electricity for around 40 houses. This unique energy source is of vital importance for the crew.
There would have to be a catastrophic accident for the station to end up without power. But even if that did happen one day, we have independent batteries. And we also have solar batteries on our Soyuz vessels. It's virtually impossible to imagine the station without electricity.
These are the crew quarters. There are 4 here. I'll show you what mine looks like inside. There's my name on it, and that's how I know it's mine. Inside, it's small, like a telephone booth. But it's pretty cozy. I have my computer for emailing my family and for calling them via Skype with a headset. I have another computer, an iPad, and the stuff I need for work. Here you just stick everything on the wall. That's how you do it in a weightless environment.
And you can see there's a sleeping bag here, which is very comfortable. The sleeping bag is fixed to the wall so that I don't float away or kick anything. And it's really comfortable to fly and float and sleep in zero gravity.
You're sleeping in a box, and you wake up, and there's your computer right in your face. And your computer has this timeline, and it's like yelling at you, get up and get to work. That's your daily life. You get up, we have time in the morning, you get up and get ready for work like you do here.
Doing your morning routine, washing a little bit, having breakfast, same as here on Earth. Usually crew gets up between 6 and 6:30 in the morning.
For meals, the astronauts usually eat dehydrated products to facilitate transportation and reduce the amount of space required for storing food.
So now our coffee packet is filled with nice hot water. We just need a little plastic straw. Insert the straw, take the cap off, and drink.
The first thing to do, once you've woken up and had your coffee, is to check the station parameters and report to ground control to say how you are and how things are operating. Then you receive instructions from ground control that might change the timetable a little. We usually plan things week by week.
To ensure the space station functions correctly, an efficient communication system is essential between the station and the Earth. In Houston, at the HQ of the American Space Agency, the teams are in contact with the astronauts almost constantly. From the control center, the engineers use telemetry to interact with many of the station's operational structures.
If you want to do anything, if you want to send a command, turn a pump on, turn a fan on, you have to go to a computer and pull up various displays and then send a command to turn that fan on. So for the crew, it's kind of a pain, but for us, it's what we're trained on. So the ISS is definitely flown from the ground from various control centers all around the world. We have a bunch of different team members all in charge of various systems, and that's only out of Houston. So we also have people in Russia, we have people in Germany, we have people in Japan. So again, we have people all around the world working, again, for sort of a common goal. But
a little better edge would be helpful. If you could tweak the holder or the sample, bump it a little bit, that would be helpful. Will do.
Each of the station's modules has ways of communicating with Earth.
Okay, this is our, it's called a PCS, which is basically information on how the station systems are doing. But most important thing for us are the comm, what is available comm-wise. And we have 4 different channels, space to ground 1, 2, 3, and 4. As you can see, it's upside down, but that's just the way it happens to be here for us. We need to talk to the ground quite a bit. They help us out tremendously. They're the ones with all the real knowledge, again, so we're just a glorified technician.
Ground control maintains voice commanding and also electronic commanding of the space station, primarily by using satellites which are in a higher orbit.
The International Space Station is constantly sending and receiving data via its satellite dishes. 36,000 kilometers above it, geostationary satellites receive the information and transmit it instantaneously to the ground. Communication is thus ensured all around the world.
Now we are in communication virtually 100% of the time that we're on board. But that wasn't the case 15 years ago. We'd communicate in little periods, like 20 minutes, when we communicated with ground control, depending on the orbit. Today we have good quality communication for professional use and for talking to family and friends. It makes for much better living.
Thanks to this communication, the astronauts are now able to share their feelings with the rest of the world.